As promised, here's our first lecture. So we take a look at this. This is just some information for chemical engineering people. If you are one of those people, go ahead and hit pause so you can go through and read this. Otherwise, we're just going to continue on. You should be getting a jump start into our reactions. So you definitely know where that information is. I believe these are actually made as required YouTube videos. That you just have to watch and comment on. So they're a little bit shorter, but they provide a lot of the generic background information that will probably be helpful in preparing for exam 3 in the final. Hopefully you watched the play pause it video, which would mean you would be able to now do this as a quiz, which we can't do as a quiz, but I'm going to ask that you go ahead and pause the video and try and add curved arrows, label the type of mechanistic step, and then if you remember what the secret code word was, that would be useful to also write down. But since it's not an actual assignment, we won't stress there. So, second request, go ahead and pause. Hopefully you now have answers. So if we were going to go through and add curved arrows, what we're trying to do is move from one reaction to the next. So I want to evaluate what is in that red line and how does it change when I move to the blue thing. So hopefully what you can tell is there's an extra hydrogen that's no longer, or that becomes there. So how does that happen? Well, I'm going to have to take electrons from my oxygen. I'm going to take that lone pair of electrons and now share it with the hydrogen. That's how I moved from red to blue. That step was merely the transfer of a hydrogen, so what we're looking at is an acid-base mechanistic step. Okay? Should be fairly familiar from Gen Chem. I have seen Gen Chem textbooks show a black arrow like this, showing the motion of atoms. Horrendously wrong. Don't do that. Okay? If we move to the next thing, we're going to move from the blue line to our orange. Again, we want to notice what has changed. So a couple things that are going to pop up as changes. Number one, this whole piece here has disappeared entirely from the structure. And one of the things that organic chemists tend to be horrendously bad at is balancing equations. We tend to not show the pieces that have left structures. Typically, in general, we don't do that. But at the same time, it's usually because those pieces that have left are not organic. In this case, water left. So if I'm going to add a curved arrow to describe that, if we go through and look at what changed, that oxygen had to take a pair of electrons. Okay? Since none of the bond connections to the hydrogens changed, we're talking about the electrons in the bond between the carbon and the oxygen. So that oxygen is going to take those electrons away. The result is that our carbon now has lost electrons. It had an electron that it was sharing with that oxygen, and it is now giving it up entirely to the oxygen, which is why we now see that positive charge on our carbon. So hopefully that makes sense. Mechanistically, what happened? Well, in this case, all that's changed is I broke a bond. Because all it is a breaking of a bond, we call this, according to Carty, a heterolysis mechanistic step. So just the breaking of a bond. Let's go ahead and move orange to purple. When we look at our orange to purple transition, what's happening, and this can become kind of tricky to see, particularly if we don't have all the hydrogens shown, so I'll add those all in a second, is that it appears that that positive charge has somehow moved locations. Okay? Remember, our arrows show the motion of electrons, not charges. Okay? So we have to be a little bit careful to understand how the electrons moved. There was a big hint given to you with that hydrogen drawn on. If we go through and look at that same carbon where the hydrogen was initially bound, we don't see that hydrogen there anymore. It's not specified. So now the question is, where did it go? Okay, where it went is actually here. And if we go through and look at all of the individual positions, there's a CH3. Sorry, that's a bit confusing to see. CH3, CH3. So if we go through and evaluate what changed, What changed was that orange hydrogen has moved locations. Okay? So how am I going to show that it has moved locations? Well, part of that is going to be what did it move with? Because if we go all the way back to the very first reaction, that acid-base reaction, we moved a hydrogen. Technically, in this case, we're not moving hydrogen, though, because we have a positive charge in our product. Okay? So what happened was that we took the electrons with the hydrogen and we moved them over to that position. So we could show the arrow that way. That could easily get confused with a variety of other arrows. So it is my recommendation, after I saw someone else do this, is that we throw a little curlicue into it to show that we're doing something a little bit bizarre. That little bit bizarre is that we're doing a rearrangement. Rearrangements are tricky to deal with. They're usually moving things like hydrogen. Sometimes you'll see methyls or larger groups, and it can become tricky to deal with. So it's helpful to have things labeled. Okay, so all we're adding is that one extra arrow. We did a rearrangement. Let's go ahead and clean up our structure for the last step. In our last step, we're going to go from purple to black. Well, what changed? What we did was we took a pair of electrons on that bromide and we shared them with our carbocation. Okay, that forms that new bond, and we'd have a final product. That mechanistic step is now a coordination. A coordination because we've now connected electrons. So it's all that happened. So if we look through our individual mechanism, we've got 1, 2, 3, 4 arrows, 4 mechanistic arrows, and 4 reaction steps. It's challenging. Sometimes we'll reference steps as reaction steps. Sometimes they'll be referenced as mechanistic steps, but all we call them is steps, so be aware of that. Another thing that could come out of this is you look at it, well, each mechanistic or reaction step required one curved arrow. That's not true. Sometimes a reaction may involve a whole bunch of curved arrows. So you're usually in a 1 to 3 range when it comes to curved arrows. But this is now effectively what we're expecting you to do in the next section, is to be able to add curved arrows to show how reactions happened, and eventually what it will become by the end of this unit, if you allow me to now erase everything, is that we will give you that. H plus and Br minus, in fact, we can get rid of that, and we'll say, what product are you expected to get? So you have to be able to reason through what happens at each of those stages and then decide, should you be doing something else? Should you be moving forward, or should it stop right there? Okay, so that's just the preview. So with that, we'll go ahead and continue on. The first chapter we're going to look at is chapter 6, which is looking at largely energy diagrams and acids and bases. So if we look at these two systems, you should be able to go through and predict which one's an acid and which one's a base. But you might notice that it's a little bit tricky because all of them have hydrogen, so they could all theoretically act as acids. And then they also all have electrons. Shown as a negative charge here, there's an implied lone pair on that nitrogen. There's 2 implied lone pairs on that oxygen, and there's a negative charge there. So they all have electrons and they all have hydrogens. So deciding what happens in our reaction becomes challenging. So let's just pick one and run with it and see what happens. So let's take a look at the top reaction. What if we went through and said this was an acid and this was a base? Okay, well, what if it is an acid? What does an acid do? An acid should donate a proton, so we should end up with SO3 with now a -2 because it's lost that H+. So this is an H+ donor. What happens to the base? Well, the base accepts that H+, so it's an H+ acceptor. And what do we get as a result of that? We would get NH4+. Okay? And we've now completed that as an acid-base reaction. We should also remember back from either Gen Chem first or second semester that SO3 minus 2 is now the conjugate base. It's not a conjugate acid because if we ran the reaction in reverse, that SO3 minus 2 would have to accept a hydrogen. And that our NH4 plus is also now a conjugate, as soon as my pen starts working, a conjugate acid. How else could the reaction have run? Well, we could have said that it did the opposite thing, in which case our HSO3 minus acted as, let's see, switch up our colors a little bit. Whoops. Acted as a base, and the NH3 acted as an acid. Okay, so if we went through and ran that system, if it acts as an acid, it donates hydrogen, and so we'd end up with NH2 minus. And if our HSO3 acted as a base, we would get SOH2SO3 because it accepted that hydrogen. So these species are interesting because they had two possibilities. So how would we decide which reaction, be it A or reaction B, which one was the preferred form? Well, to do that, we would have to evaluate the stability of each of those individual results and try and come up with some prediction. So let's give you a chance to think about it here. Okay, so let's decide. How do you think you want to go through and address this? Okay. My recommendation would be to take a look for the most reactive thing possible. Okay. In this case, I don't want to focus in on the middle because the middle is where everything was happening anyway. I'm going to focus in at the products. And in particular, I'm going to focus in at these two products. Okay. I'm going to look at those two because those two have electrons. And in OChem, we're concerned about transferring electrons. So those are going to be my primary focus. If I'm going to have the reaction run as B type, I need to form SO3 minus 2. If I run it as A type, I need to form NH2 minus. So how would I decide which pathway was better? Well, which of those two is better able to stabilize that negative charge? Okay? That becomes a much more challenging question, but you should be able to figure that out based off of some of your experience already, and you should know that this one is more stable and, interestingly enough, less negative than our NH2 minus. So this one is less stable, okay, and more negative. Okay. And yes, I didn't pick the greatest example for that, but it's going to work out. And because of that, we would guess that reaction B was the more likely pathway and not reaction A, because I want to form the more stable results. That's what we're trying to do with our acid-base reactions. So when we think about our acid bases, this is effectively what we're doing, about labeling an acid, labeling a base, and running the reaction, and trying to come up with some predictive abilities. Some of those predictive abilities you may not be comfortable with yet. You will get comfortable with them. We'll spend some time looking at them. Okay? Some of the definitions that we've got to watch out for. You used to have the Arrhenius, and I would argue Arrhenius is the only definition you've really used in Gen Chem. You've got H plus donors as acids and OH or hydroxide donors as bases. One thing I want to throw in there that is extra confusing would be a substance like CH3OH or methanol. According to our Arrhenius definition, that is not a base. Okay? That is not hydroxide out there. For it to be hydroxide, it would have to be bonded to a metal. It's not. So it's not a base according to our Arrhenius definitions. This definition, while useful, say, in reactions run in water, it doesn't work so well for reactions run in organic solvents. And so someone went through and expanded that definition a little bit, and this is where we get our Bronsted-Lowry definitions of acids and bases. Okay? Because H plus donors and H plus acceptors is a bit tedious, we shift that to proton. Okay, so our Bronsted-Lowry definition now talks about the transfer of protons back and forth. And that helps us because it simplifies our definitions a little bit. We don't have to be looking for hydroxide, which, as I pointed out already, is a challenging thing for most people to pick up on. Okay? And we just have to look at what's happening with our H pluses. Once we've established that, we then have to come up with ways to rank and predict things. Okay? So you should be able to go through and evaluate these things according to acids or bases. So take a second to go through and decide. Again, I'll give you the opportunity to pause here. And if we continue through to try and decide, HCl should stand out as a clear acid. NaOH should stand out as a clear base. We then move into some kind of gray areas. You might remember from 130, a hydrogen in front was typically a red flag for it being an acid. We move to the next one, though. I don't see hydroxide. So what is it? Could it accept a hydrogen? Well, if we break this down into a formula a little bit better, we have sodium ion next to our acetate with a negative charge. What could be attracted to that negative charge? Well, a positive hydrogen. If a positive hydrogen came in and interacted with that species would now be a base. And what would it have formed? It would have formed the conjugate acid in 3. So yep, that one is a base. When we move to the next one, sodium and chloride. Okay, we might go through and have a little bit of struggle with that one, but again, we could write this out, Na plus and Cl minus, and we might try and do similar things. Could it react with a hydrogen? Well, if I put a hydrogen next to that Cl, I would have HCl, and HCl is a strong acid, so that can't form. Whoops, that's not what I meant to do, but it worked. Which means NaCl is really neither. Okay. What happens when we hit CH4? Well, CH4 has hydrogen, so couldn't it act as an acid? Okay. Well, if it acts as an acid, it would produce H plus and CH3 minus. Well, is CH3 minus something that's stable? Okay, which is now a new question. Should we be concerned about stability? It turns out, well, yes. Okay. If that species is not stable, then this one can't form. If H plus can't form, then this species, not an acid. Okay? So stability does become important. And when you evaluated things back in Gen Chem, you didn't really trip up on those definitions too much. You kind of just ignored them. Okay? They're now going to become more relevant, and you're going to have to be able to think about those relative stabilities. Okay? CH4 is going to be neither. It can't act as an acid, as we just walked through. And then also to act as a base, what would it need to do? Well, it would have to be able to accept more hydrogens. If we draw out a Lewis structure for CH4, there is no space to put an extra hydrogen, because if I added a hydrogen on there, I'd have a pentavalent carbon, which doesn't make sense. So it doesn't act as an acid or as a base, really. NH3, we might go through that same argument. NH3 to act as H plus, to act as an acid, we'd have to generate something along these lines. Well, NH2 minus is not particularly stable. If it's not stable, then this can't form. If that can't form, then that's not an acid. Okay, so we've got these kind of sequence steps through. So we might go through and say, well, that's neither again. Except, if we look at our Lewis structure for NH3, what does it have? It does have that lone pair of electrons. That lone pair of electrons can donate or share to a hydrogen, which means NH3 can act as a base. CH3OH becomes a whole nother fun can of worms to deal with, because that one has that hydrogen on it. It also has lone pairs. Depending on the situation we're in, it could really act as either. Okay? It's not going to be a strong acid or a strong base, but it's going to have some flexibility with it, which means what we're going to start to notice is that with acids and bases, we can make something be an acid as long as we react it with a strong enough base. We can make something be a base as long as we react it with a strong enough acid. Okay? For the most part, we're dealing with relatively neutral systems, so we don't have to stress a whole lot about that, but we'll see it pop up here and there. Okay? So there are definitions, these aren't our definitions. We have an extra definition, our Lewis definition. Lewis went through and noted that the Bronsted-Lowry and the Arrhenius were both not explanatory enough for all reactions. So Lewis switched it up, and instead of looking at the atoms transferring, we looked at the electrons transferring. This now allowed us to apply acid-base definitions to everything. And when I say everything, I mean literally everything. So broad, in fact, that and potentially powerful, that when Lewis was nominated for Nobel Prizes, they said no because his definitions were just too big. They encompassed just way too many things. So, in kind of running counter to, say, popular organic chemistry lecturing, I'm going to argue that our Lewis acid-base definition is too broad to use because it applies to too much. And instead of having to say, I'm talking about a Lewis acid or a Bronsted-Lowry acid, I just want to be able to say acid. And when I say acid, I'm very particularly referencing the Bronsted-Lowry definition. And when I say base, I'm very particularly referencing the Bronsted-Lowry definition. What about those cases, say in that bottom reaction, where that bromide shares with that positive charge? We are transferring electrons. Okay? How do I explain or label that? Well, that labeling, if I went to the Lewis definition, would also incorporate acids and bases and just becomes confusing. So we add a new term. This is where we get electrophiles and nucleophiles. So our Bronsted-Lowry is centered very squarely on the transfer of protons. If I'm looking at a transfer of something other than protons, for example, electrons, then I'm going to reference electrophiles and nucleophiles. Okay? And that's the intent behind that. I don't want to use the Lewis definitions because, again, the Lewis definitions use the same terms, acids and bases, which then means you have to add extra clarity. So if we stick with acids being proton donors, bases being proton acceptors, electrophiles being electron acceptors, and nucleophiles being electron donors, we've got the basics for all of our reactions, or 95% of our reactions. And that's what I want you to be able to deal with and to manipulate and talk about. So we end up skipping our Lewis definition for the most part in favoring of Bronsted-Lowry acid bases and then electrophile, nucleophile. I already started to at least hint at the reactions down below, but we've got technically 3 reactions shown. Go ahead and label them out using curved arrows and label as either acid, base, or electrophile, nucleophile. So again, take a minute here to pause. And now I will go through and layer over the top. We're transferring the electrons. Notice here we've got 2 mechanistic steps, and or 2 mechanistic arrows in one reaction. That first species acted as a base, and the next species acted as an acid. Okay? The only thing being transferred were hydrogens, or hydrogen ion, in particular protons, so I could reference that as an acid-base reaction. Okay? And in particular, a Bronsted-Lowry acid-base reaction. If we move to the next one, things get a little bit more complicated. Bromide takes the electrons from that other structure. We don't really get a Lewis or Bronsted-Lowry reference here. We're just breaking a bond. Okay? There isn't a transfer of one atom to another. So we don't really have a way to label that one. If we move to the next step, however, the bromide shares electrons with that positive charge in that single mechanistic step. Whoops, helps if we actually reference the right thing. The cyanide shares electrons with that positive, and what we're getting there is that cyanide now being attracted to a positive charge. What subatomic particles are positive? That's right, nuclei, and so it is a nucleophile because it is loving nuclei. That positively charged species is an electrophile because it is attracted to negative things, our electrons. And if we run so when we look at our bottom reaction, we're really looking at a Lewis definition acid-base reaction. That could get confusing with the Bronsted-Lowry. That's why we can just reference it as electrophiles and nucleophiles. Okay? So hopefully that kind of clarifies some aspects behind that. This is really just a summary of arrows so that you are aware of what they are and when to use them. We will be using all of them, and we have used most of them. I think the one we haven't used yet is that single electron arrow. So you will be seeing these. You need to know when to use them and what they mean. The big confusing one for most people is this double-headed arrow, the resonance arrow. I've seen lots of general chemists use that to represent equilibrium. It is not an equilibrium arrow, and people that use it as an equilibrium arrow should feel bad. Learn to find a better arrow. That is only used for resonance. The equilibrium is the double arrow shown above it. Okay? Sometimes the curves won't be super huge, so be aware of that. You could have a curved arrow that isn't actually curved, but you still need to know it. Okay, or differentiate it. When we look at our curved arrow notations, we have to make sure that we use them appropriately. When we're talking about curved arrow usage, it's looking at the bond breaking or formation, okay? And it's really only involving valence electrons as far as we're concerned in our mechanisms. These are the movement of electrons. We see the presence of atoms already shown in our reactions. So what we're going to try and do is use the arrows to draw attention to the electrons. And that becomes the tricky part, is because we rarely, if ever, show electrons. At least early on in this unit, and maybe for the rest of the semester, those reactions will be balanced to help you see where the pieces are changing and how things are shifting around. For sure, the smart work is designed to help you focus in on what electrons are moving and where they're going. So we've already seen these. It's nice with colors because we could go through and show that those electrons are now sharing, making that new bond. Okay, so the colors can help add emphasis to what's going on with that. You've seen curved arrows before. This is now different because these curved arrows are being used to show how sigma bonds are being broken and how sigma bonds are being formed. Okay? But we've used curved arrows before. We used them when we talked about resonance. Okay? In resonance, we were moving lone pair or pi bond electrons around. Okay? And we could move them from where we had a source, the pi bond or the lone pair, and move them in directions where we could move other things, places that were lacking electrons. So in that process, we never broke the sigma structure. Those were all maintained, and we had very particular rules on how we could go through and do it. When we move to mechanisms, we're using the same arrows, but now we're talking about how we can break a sigma bond. And one of the questions that's going to pop up is going to be, it has to be an easy sigma bond to break. Okay? And that is a challenging question, at least initially. Okay? So if we took a look at the first step here, okay, why is that sigma bond the easiest bond to break in that whole structure? Well, bromine and carbon, bromine being very electronegative, is already withdrawing those electrons. So if we use electronegativity differences to help key us in on that reactivity, we can start to predict how things are going to shift around and move. Okay? So that helps us to acknowledge that that would be our first step, because the bromine's already starting to withdraw electrons. Other things that we could consider that I arguably shouldn't be talking about yet, because we're not going to look at these, would be the pi bond. The pi bond is higher in energy. Why not have that pi bond react? Okay, well, a lot of that is going to come down to what else is present. And if we looked at this as an overall reaction, so we removed some of the pieces from this, we're talking about reacting this with cyanide. Oh, and that was just sloppily drawn, but I got it there. Okay. That purple bond of our pi bond is electrons. If we go through and look at the rest of our reaction, we're reacting it with cyanide, which is also electrons. Okay. What are the odds that electrons are going to interact with electrons? Slim to none. So it doesn't make sense to have that pi bond react first in this circumstance. Okay. But if we change the conditions, where instead of there being a negatively charged species we're reacting it with, but a positively charged species, that's going to drastically change how our chemistry is going to occur, because that's going to force a different mechanism or a different result. Okay? So you should be considering those balances or imbalances of charge when you're looking to drive a mechanism. We've got another kind of random quiz popping up here, so I will give you a second to again pause and decide which is the strongest acid. So yeah, there's that long quiet because you should have paused it. In theory, we're good, so let's go ahead and evaluate. We have H+. Whoops. Just testing you there. HCl, HF, and then here. So in theory, you should have gotten all of those. Okay? Maybe you've got that memorized. Maybe you understand the rules, or maybe you just have a reflex to help you through that. Okay? The process that we should be considering when we look at these would be to go through and decide what would happen if it acted as an acid. So if I had H3O+ act as an acid, I get H+ and H2O. If I have H2O act as an acid, I get H+ and OH-. Okay? In both of those cases, I'm ending up with H+. So trying to decide which of those two species was the stronger acid, I actually don't want to look at the H+, because they both produce that. What I'm actually looking at are these two species. And I use those to decide which one was the stronger acid, H3O+ or H2O. Okay? Well, if I'm going to form a significant concentration of H+, I also have to form a significant concentration of the conjugate base. Which of those two conjugate bases is more likely to form? H2O. It is more stable than the OH-. Why is it more stable? It's not charged. So we could evaluate the conjugate base stability to decide which one's the stronger acid. Earlier on in these slides, I threw a bunch of substances at you and just said, tell me which one's an acid, a base, or neither. Most of the questions that you will encounter won't be just absolutes. They'll be comparisons. You have to be able to compare each of those structures to decide which one is the stronger acid than the other. Why do we need that? Well, remember, at the end of that previous sequence of slides, we encountered methanol. Methanol could have gone either direction. This way, we now actually have it established which path to be looking at, because we're making a comparison between two. So if we clear all that away, I'm probably going to regret that, but let's see if we can figure this out. We could evaluate this one was the stronger acid because our conjugate base was less charged. Well, what happens if we move to HF versus HCl? If we run the same idea and just look at conjugate bases, I get F minus and Cl minus. Okay, well, why is Cl minus better than F minus? Okay, why is it more stable? Well, what is the difference between F minus and Cl minus? This is where we go all the way back to our very first lecture, and we talked about trends in the periodic table. And the trend that we saw when we looked at F versus Cl on our periodic table is that Cl is lower on the periodic table, which means it is bigger than F. Both of them are reactive because they have that extra electron. That extra electron is highly charged and highly dangerous. If we touch that, we get shocked. Which of these circles, if you were forced to, would you put your hand into? Probably go with the Cl one because it's bigger. You'd be less likely to get shocked. The same thing's happening for our electron. That electron has more space and is therefore more stable. The chloride is a more stable negative than the F minus. What does that mean for us? Well, the HCl is now the stronger acid because the conjugate base was less charged. Okay, well, it's starting to seem a little bit redundant, so let's take a look at the next one. We should end up with HCOOH being our stronger acid. Takes a little bit to draw this one out, but if we looked at a Lewis structure, hopefully we'd be able to identify that hydrogen is our stronger acid, and you might ask why, which is a really awesome question. Okay, so if we don't know, let's attempt to draw it out. If we remove the hydrogen from, try and maintain the same structure, the carbon, we'd have the negative charge there. Which of those two is more stable, a negative carbon or a negative oxygen? The negative oxygen because, not size, but now a difference in electronegativity. So the purple one doesn't make as much sense as the red one. Okay, well, what happens if we compare that now to water? Why is the boxed one more acidic than water? Why is it more stable? Okay, well, what happens? They're both negative oxygens, but everybody's favorite 8-letter word or 9-letter word, you can count and figure it out later, has resonance. That resonance stabilizes that negative charge, thereby making the conjugate base less charged. Okay, notice in each of these cases we're coming to the exact same conclusion. We're making the conjugate base less charged. The more less charged it is, the more likely that is to act as an acid. And we're just evaluating different aspects as we move through this to decide which one was more or less stable. Okay? It is those thought processes that you need to be moving through, not just going based off of a reflex gut. Okay? If you want a reflex gut, that's fine too. But ideally what we're looking at is trying to come up with some kind of rule set that would allow us to explain these. Okay? That rule set is addressed in Gen Chem. Okay? At least it's addressed in 152 whenever I taught it. Okay? We're looking at ranking acidities, and you had 4 rules. Down a column, stronger acids have larger conjugate bases. Across a row, stronger acids have higher electronegativities. And then you encounter these weird oxy acids rules. And ultimately, all of these things are giving you something to memorize so that you don't have to think about and drawing out the reaction. You should be drawing out the reaction because that's 90% of what we do in OChem, is how do we draw and predict these things out. Okay? So spend some time to start drawing them out, and hopefully you will evaluate and find that these rules make sense. Okay? So if we think about that larger conjugate base one, that's where we were saying F minus versus Cl minus. Okay. If we looked at electronegativity, we were looking at, the example we picked was oxygen versus carbon. Oxygen negative versus carbon negative. Okay. notice that there's a rule 1 and a rule 2. We evaluate size before we evaluate electronegativity. Okay? That is important. You need to be following that. What happens when we move into the rule 3 and 4 that I've now crossed out? Okay? When we look at rule 3, we're saying HOX, HOCl. Okay? We're saying that this one is more acidic than the one underneath. HOF is more acidic than HOCl because F, our atom X, has a larger electronegativity. Okay? If you move to rule 4, okay, rule 4 now goes through and says, well, what if you have more oxygens on there? How does that affect the acidity? Well, the one with more oxygens becomes more acidic. Okay? Really, those two rules, and I would argue on my slides here, I have these reversed, okay, are getting at the exact same thing that rule 1 and 2 were looking at. Okay? If we look at what was rule 4, why would increasing oxygen increase the acidity of that OH bond? Okay, well, if we looked at a proper Lewis structure, and I'm going to pause the video while I think through the proper Lewis structure, and then you can do the same. Hopefully you ended up with a structure with a whole bunch of double bonds. If we remove that hydrogen, we'd have a negatively charged oxygen, and that would not be stable, except the more oxygens I put on there, the more potential for resonance. And I'm now moving those electrons and sharing them across a larger space. Resonance is effectively size. It's the larger conjugate base, okay? Because the electrons are now allowed to move across a larger area. If we move to rule 4 is effectively an inductive effect, okay? The more electronegative an atom further away is. So really all we're really looking at when we look at our rules is we want to minimize charge, and what it's going to come down to, if we really, really want to utterly simplify this down, is that rule 1, I want to evaluate size. Rule 2, I'm going to evaluate electronegativity. Okay? And in those cases, what I'm evaluating is the size and electronegativity of the atom where the hydrogen was. Okay, so atom after hydrogen donation. Okay, and then when we move down to rule 3 and rule 4, well, this is really just size again, but it's resonance. And we move into rule 4. Well, rule 4 was electronegativity again, but we used a fancier word. We used induction. Okay. Well, those are really just saying what is happening at the molecular level. So we're really just evaluating how is an atom affect stability or an atom affect charge, and then how does the molecule affect charge? Why would I look to the atom first? Well, that's what you should be doing too when you go through and study. You look to your own skills first, and then if you don't know, then you go out. Okay? And you gain that knowledge somewhere else. That's kind of just how life happens. When you learn how to walk, you just try and walk on your own. When you fall flat on your face, then you start reaching out to get help from other people. Okay? So the same thing's happening here. So we're looking at how those things stack and affect things. Okay? This would be a lot more fun in class because we'd make it a fight for half the class gets the left structure, half the class gets the right structure. Okay? But since you're doing it all at home, we've got 2 structures. Figure out the most acidic in each of those structures. Again, take a minute to pause and figure it out. I might even build this into a play posit to force you to pause. Since you've had a few seconds to go through and evaluate, hopefully what you'll notice, at least for that first structure, is that we have a hydrogen connected to an oxygen versus hydrogens connected to carbon. Okay? If you were really pioneering, you might say, but isn't that green hydrogen different than the red hydrogen? And isn't that orange hydrogen different than both of them? And I would be like, yes. Yes, that would be true. You are making life more difficult, sort of, for the sake of this assignment, because if we compare these 3 hydrogens to this hydrogen, what's the difference? We're talking about an O to an H versus a carbon to an H. The difference right away jumps out at the oxygen, which means the oxygen is going to be the more acidic one anyway. Okay? And I don't have to evaluate green, red, orange connected to the carbons. That would be a fun advanced question for you to go through and think about and come up with your ranking system. I'll reveal that in a little bit. When we go through and look at the other structure, we get the same kind of system. We've got an oxygen connected to a hydrogen versus carbons connected to hydrogen. And again, we run into the same issue. We could potentially go through and label the crap out of our carbons or out of the hydrogens connected to our structure. Okay? Which is a good thing to be thinking about. That proves that you were paying attention in the spectroscopy aspect of the class. At this level, that difference is so nuanced that we usually don't have to worry about it, and we can really just say we're comparing a hydrogen bonded to oxygen versus a hydrogen bonded to carbon. Okay? And to that end, we now have 2 hydrogens to evaluate, either the red hydrogen or the orange hydrogen. Well, which one's the stronger acid? That's right, the red hydrogen, because if we removed that hydrogen, we'd be putting a pair of electrons on that oxygen and a negative charge, and we have the potential for resonance, which means the structure to the left is more acidic than the structure to the right. Okay? If you've done a good job in recognizing your functional groups, you might have keyed off on another big piece of information to hint you at this. That red structure versus the blue structure. The blue one's known as an alcohol, and the red one was known as a carboxylic, everybody together now, acid. Which one's the more acidic? Probably the one we call an acid. That's why we've called it an acid. Okay? So what we're considering is how that charge affects the overall structure and how we manipulate and deal with it. Okay? I did say we were going to discuss real quickly the answer for our green, blue, and orange hydrogens. The green one is likely to be the most acidic, followed by the blue, followed by the orange. Why? The rule that we would be using there would be rule 4 off the previous page, which is an induction, okay, an inductive effect. And arguably you could say the green one might even have a little bit of a resonance effect too. So here's all of our rules nicely listed out. You'll notice that we do have a 6th one on this list, and it has a weird name associated with it. If you check the internet, you might hear reference to this kind of sequencing of rules for deciding acidity. Okay, I would argue that calling it acidity is way too vague. Okay, what we're doing is ranking reactivity, because this applies to everything. When it comes to second semester, I will be asking for these 6 things virtually every class, because I want you to be thinking about and manipulating them. So in that list, we'd start charge, size, electronegativity, molecular effect, our size, which is resonance, and then our molecular electronegativity, which is induction. Okay? Because these are so critical to understand and memorize and know, people go through and try and come up with mnemonic devices to memorize the order in them. And so they start with a charge, and they say, well, C. Okay, we'll skip the A for a moment. They get R, you get I, and then you get O. Okay, well, they needed something to go in between. And between a C and an R, they needed a vowel, so they threw in A. And what they were referencing is an atom effect. Charge is an atom effect, so I find that incredibly dumb. Okay, R for resonance, I for induction, and then O, I have no idea what they're talking about. And so I said O carp, because if you're digging into that, it's usually a bit of a challenging thing. There are all sorts of other things that happen in there, substitution effects. Okay, so there's a bunch of stuff that can happen in that category. They tend to be much lesser effects, and less tested on for the most part. But if you wanted to kind of memorize a mnemonic device that sort of half makes sense, Cario can work. Personally, I would expect charge, size, electronegativity, resonance, and induction. Okay? In first semester, we use this to apply to acids. Okay? Again, I think it applies to everything, not just acids. When it comes to second semester, we start talking about bases, and in particular, we start talking about the base of nitrogen. Okay? And the nitrogen functional groups tend to be a second semester functional group, which is why we don't talk about base strength so much in first semester. And what happens is that people try to apply their knowledge to second semester, and what they end up doing is screwing up the base ranking system and go, oh, you have to memorize a whole nother thing. You don't have to memorize a whole nother thing. Okay? When looking at acid-base strength, we have to realize that acids and bases are opposites of each other. These 6 rules that we're looking at are just the things that you should be looking at to evaluate based off of the definition of acid or base. When we look at acids, we typically evaluate the conjugate base. Why would I bother to look at the conjugate base to evaluate my reactivity? Well, again, organic chemistry is about the transfer of electrons. Why look at the conjugate base? What does the conjugate base freaking have? Electrons. That's why we look at the conjugate base when we think about acids, because we can see the electrons. They're marked off as this negative charge. When we move to bases, all of a sudden everybody freaks out and goes, well, it's a whole new system, and now we've got to start looking at the conjugate acid. Okay. Before you start freaking out too much and saying, applying that exact same system, why would I look at the conjugate acid? Remember, the whole thing was to look for the electrons. Where are my electrons? They're on the base. There's no need to look at the conjugate acid. I can start by looking right at the base and saying, are those electrons more or less basic, based off of my 6 rules. Okay? And so because there's this subtle tweak to it, I think we overemphasize acid rankings in first semester, which then means everybody gets it wrong in second semester when we start talking about base strength. Okay? Realize that these rules apply to everything, not acids, not bases, everything. Okay? They also apply to nucleophiles and electrophiles. This is why one of the biggest things that you can do to help yourself out would be to memorize the sequence of things that you should be looking at evaluating, memorize the definition of an acid, memorize the definition of a base, memorize the definition of an electrophile, and memorize the definition of a nucleophile. So that way when you go through and run a reaction and you need the most electrophilic, you've memorized what an electrophile meant, so you know what electrophilic means. You then know most is based off of which one of those rules should you be evaluating to get to that most category. Okay? So right here are the big key things that you should be memorizing. So much or so important that I'm actually going to go through and take a minute to pause and write those out nice and neatly. The beauty of the pause button, there are all your important pieces outlined, tied together as best I can do it. You should make sure that you've got these things nailed. Okay? After that, it's just an application of these rules, okay, to drive pretty much everything we do. Okay? With that, I'm going to go ahead and move on. Can we quantify all of this? Yeah, we can. So if we went through to look at these individual reactions, we could evaluate the differences and decide which way our reaction should go. So you might remember from 152, you've got equilibrium arrows that you could be looking in each of these and try and predict which way your equilibrium would favor. So if we went through to evaluate these, we would actually find that both of these kind of actually heavily favor the reactant, some a little bit more so than the other. For instance, this one is ridiculously favoring the reactant. How would we decide the kind of magnitude of those arrows? Because notice these aren't perfect equilibrium arrows, evenly spaced. How do we know which way it should go? Well, one way to do that would be to use the information that we just identified on establishing stability of those individual pieces. The other way we could use it would be going up and looking up pKa's and equilibrium constants and all of that to figure all that fun stuff out. Okay, largely what you did in 152. Okay, as super exciting as that is, you don't have to quantify it all that carefully. You do want to be considering where that information is coming from, because that's ultimately the numerical underpinnings of those rules we just evaluated. Okay, so those rules have meaning because someone went through and did all these equilibrium constant stuff, okay, which is awesome and fantastic. And you know me, I love numbers to death, and it's great, okay, but we don't really need to use them all that often, okay. So I do want you to know that you should be able to pull out an equilibrium constant, products over reactants. If we looked at Ka's, it simplifies things out a little bit, okay, and we're looking at those individual relationships, okay. So one thing that does come out is that you will probably need to know relative pKa values. Why pKa's and not Ka's? Well, as you should hopefully remember from 152, your Ka's were these big exponential things, 10 to the negative 7th, 10 to the 3rd, big powers of 10. Okay, that's confusing to deal with, so we converted to pKa's, negative logs. That brings in a negative sign, which gives us the inverse, and so now we have to remember our pKa's. Big pKa's are things that are very weak acids. Small pKa's are now strong acids. Okay? So we could go through and look at the balance of products and reactants based off of knowing something about our pKa's. Okay, what do I mean by that? Well, let's double back through so we can clean up and look at our reaction. I want to look at acids. So in this top reaction, this species is acting as an acid because in the end result, its conjugate partner has lost a proton. Okay? And then the other species, H2O, acted as a base to produce the conjugate acid. So when I'm evaluating which way this reaction goes, what I could be doing would be looking at pKa's. Well, the pKa of our starting acid is about a 4.2. The pKa of that ending acid is a negative 1.5. Okay, well, I just had you real quickly pKa scale. The smaller pKa was the stronger acid. Okay, so based off of that information, which way should my reaction favor? Should it favor the reactants or the products? Well, reactions go towards more neutral, less reactive things. This reaction heavily favors reactants because we're looking at, 10 to the power of 5 order of difference in stability. Okay, so that meant we looked at pKa's. Well, we said that's not fun to do, right? We could try and pull out and use our rules that we just came up with to evaluate things. But in our rules, that ranking system, we were looking at electrons. So I want to change my focus from now looking at acids. I'm going to look at it in terms of the bases. And how does that evaluate? Okay? So my starting base versus my ending conjugate base, and I want to evaluate stabilities. Well, what is the difference in stability between these two structures? Well, that difference in stability is that this one has a neutral charge, this one is a negative charge. Which one's more stable? Well, according to my charge rule, the very first thing in my list, the 0 is less charged, so the 0 is more stable. And which way does my reaction favor? Notice again, heavily towards the reactants. So I don't have to dig to pKa's. I can use that stability of charges to help me predict something about reactivities. Okay, so that's kind of cool. At least I think that's kind of cool. So there's all the rules. There's that red box rule again so that you've got that nailed down. I would recommend that you memorize some common pKa's. Okay, so these are the pKa's of particular functional groups that I think are important to memorize. We will see more as the semester goes, but these are kind of the big ones that you should nail down. Okay, I do want to call out the weird one in the middle. Amines sometimes get labeled as 35, sometimes labeled as 9. Okay, where that is coming from has to do with the reactivity of amines. Amines are not acids. Okay, first and foremost, that's the issue. Amines are bases. So if it acts as a base, that nitrogen accepts a hydrogen. And in so doing becomes positively charged. It is now an acid. So when you look up the pKa for amine as a functional group, you have to be careful in what they're referencing, because the amine isn't an acid. Okay? So when they say the pKa is 9, more acidic than water, what the hell's going on? What they're assuming is that what you're asking about is not about amine, they're asking you about ammonium. And the ammonium ion has a pKa of 9. If you wanted the pKa for the amine, okay, that's removing another hydrogen, making a negatively charged species, which is incredibly unstable, which is why they're like, you couldn't possibly be asking for that, because that would be silly. Why would you do that? Well, don't judge me. I'm asking for a valid reason. Give me the answer. The answer in that case is a pKa of 35. So depending on where you are referencing amines, you may see a pKa of 9, you may see the pKa of 5. Just because I always do it, really I think this confusion is going to come from my favorite category, biochemistry, because in biochemistry, we look at amines in amino acids. Okay? And it is that amino acid functional group that's getting us that pKa of about 9. And really they're referencing the ammonium species acting as the acid. Okay, so be aware of that. I was going to try and push a little bit further on, but I think we've covered enough to do with acids and bases for the moment. And look at that, officially 15 minutes early from when class is supposed to end. So we could have kept going. Thanks for listening as far as you did. I will try and be getting more out as the semester or the rest of our weeks go. Thanks for listening.